Hello YouTube, this is my first video in which I'm going to explore the concepts of what we call quadratic functions. So kind of getting away from the linear functions or lines and getting into quadratic functions or parabolas. So let's go ahead and get started by defining what we mean by a quadratic function. Now first things first, when you hear the word quad, typically or the prefix quad, people think of 4. It has nothing to do with that. It's just this what we call any function that has the form f of x equals ax squared plus bx plus c, where a is not 0. So a couple things really quickly. Recall that f of x equals, that's just the same thing as saying y equals at a given x value. And also this, we say a is not 0, and the reason why I kind of want to explore why we do not allow a to be 0 is because of this. If I had f of x equals 0, 0x squared for my a value there, plus bx plus c, then you'd have something that was just this. We'd say bx plus c, but of course, you know, I could use different letters here if it makes you more comfortable, mx plus b or bx plus c, but you'd have something that's linear in the first place and not quadratic. So we identify quadratic things as being anything of this form here, but basically you can identify them easily because they have an x squared. X squared graphs tend to have shapes that look like these parabolas here. So we say the graph of quadratic function is called a parabola. You just need to know that these graphs here are called parabolas. But I say here, for example, the graphs of y equal x squared and y equal negative x squared are actually shown on the right. Now I know these are shown on the right, but I find it's valuable if we actually take the time to create a table of values and maybe graph a few points on our graph here. So if I were to create a table of values for y equals x squared, a good set of values are these. And it's just kind of good to explore these because what you're doing is you're plugging in, let's say, negative numbers into a spot that's being squared or an input that's being squared. So if I were, for instance, to plug -2 into my function, I have this thing squared. We're plugging in this first -2. What I want you to notice is this, you know, when you square anything, you're necessarily going to make it positive again because squared, of course, means times itself. So we get -2 squared, we'd actually end up with an output of 4. Okay, so we get 4. If I were to square my -1 now, -1 squared, well, -1 times -1 is 1, so I'd get 1. Square 0, well, that's kind of an easy one to talk about. 0 squared is 0. But if I square my 1, okay, so square 1, what do I get for an output? I get 1. Square 2, you're going to get 4. The thing is, you'll notice that all of our outputs here are positive, and it's not necessarily always the case, but that is the effect that this squared term has on quadratic functions and what is necessarily gives them their U-like, parabola-like characteristics. So if I were to sketch this now, you see very similar to the graph that I have up here on the right, or the top left there. I say we went from -2 out to 2 going by ones. -2, -1, 0, 1, 2, 0. But we say we went up to 4, and necessarily in this case, but we'd say 0, 0 was on our graph. That was one of our solution pairs up here. Another solution pair was -1, comma 1, -2, comma 4. And we say 1, 1 was also on our graph, and 2, 4 is also on our graph. So not only do they have this U-like shape, but one really important thing to kind of point out about them is that they're symmetrical. So we're going to describe the anatomy of parabolas here very, very briefly. In terms of what are some points I want to know about every single parabola. First things first, you want to know that this bottom part is called a vertex, this lowest or highest spot. And we say the vertex in this case is given by 0, 0. You'll notice I put a V out front. We typically label points with letters, so we'll call this the point V, and that is the point 0, 0 is our vertex. Another key characteristic that I want to point out here is simply this. We say since it's symmetrical, we could pass a line, oops, let's do this new color. We pass a line down the center of it, and it's important to note this line passes through the vertex, but this has a name. It is referred to as the axis of symmetry. We shall, for the sake of my videos, refer to this lovingly as the AOS. And the important thing to note about the AOS is that it's always an x equals equation, since it's a vertical line running through our U's. And it also passes through the vertex, so it has to have, remember this, it has to have the same x value as the x value of the vertex. That's kind of nifty, okay? And so we say, here's our parabola here. Very, very quickly, if we were to now sketch in y equals -x squared, which was the other of our two graphs here, just really, really quickly making a table of this. The reason why I'm doing this is because people tend to mess up with negatives. So if we were to use the same set of domain values or same input values, in this instance, when I plug in -2, now the thing that's important to keep in mind is this squared right here only applies to the x. If I had been meaning to apply it to the x and the negative, I would have placed parentheses around them, but it only applies to the x. So what this means is when I put inputs in, that negative is still out front. So it doesn't matter that I put in, say, a -2, this -2 right here into here. When I square the -2, I get 4, but I end up with this -4 because that negative out front was carried down. So in this case, I'd say I end up with -4. If I were to put in -1 now, -1. -1 squared, of course, is 1, as we got before, but with the negative out front, it actually is a -1 output. And -0 squared, of course, is 0. If I put in 1 squared here, 1 squared, I'd get 1, but the negative out front causes this to be a -1. And then the same thing with our 2 here. So sketching this in, I know it's kind of cluttered, but I go down 1, 2, 3, 4 on our graph here. We had 0, 0 on this graph. 1, -1 was one of our solution pairs here, 1, -1. We also had -1, -1, so we see the symmetry again. And then 2, -4, and -2, -4, and so we get this downward opening parabola. So I guess I want you to notice this. They both had the same vertex. They both had a vertex at 0, 0, and they both had the same axis of symmetry. So I'm about to explore the effect of our graph here when we put different a values in front. I know we haven't talked a lot about a, but looking up here at our definition, we said a was like this value here. These both have a values in front of 1 here, and this has an a value of -1 if you want to explore that, but changing the a value. But before we do that, we say what are the vertex and axis symmetry of the graph of y equals ax squared. We can go ahead and say this. We say the vertex is at 0, 0 of any graph that's just y equals ax squared, and then the axis of symmetry, the AOS, is at x equals 0. So good things to keep in mind. So now let's explore this fourth question down here. Describe the effect of a on the graph of y equals ax squared. So what I've got a list of functions here that I want to graph. 1/2 x squared, 1x squared, 2x squared, and 3x squared. But we're actually going to start by graphing y equals just x squared, y equals 1x squared to be precise. So if I zoom in here a little bit, you see the graph that we just got done kind of sketching, but we say 0, 0, 1, 1, 2, 4. If we were to, square 3, we'd be up here at 9. Square 4, you'd be up at 16, but it's getting steeper and steeper. What I want to do is kind of compare all of our other graphs with different a values to this basic graph of y equals x squared and say, well, what happens when I'm doing this? So if I type in now y equals 1 divided by 2, or 1/2 x squared, I want you to see this. These two graphs, there it is, these two graphs have the same vertices. They have the same axis of symmetry. But you'll notice the second graph is a little bit wider than the first one. The very next graph we're going to make is y equals 2x squared. And when I graph this in, you'll notice it's a little bit skinnier. And so the question is, well, why is this happening? Okay. How about y equals 3x squared, which is also on that list of functions there. It got even skinnier. If I might speculate at this point, if I wanted a really skinny graph, what could I take x squared times? We say y equals 10x squared. That's really skinny. But what I want to kind of point out is this. The bigger that a value is, now I say bigger, okay, you're noticing the graph gets skinnier and skinnier. What caused then the first graph to be very wide? So I don't know if you can see my mouse up here. We say it says 0.5x squared. And of course I graphed 1/2x squared. But the fact of the matter is this: if I wanted a wider graph than a half, the thing is the graphs that were getting skinnier and skinnier, the a value that we were taking those times, let's pop back over here. We say like on 2x squared and 3x squared, the a value here is 2, or I'm going to write 2/1, and the a value here is 3, or I'm going to write 3/1, whereas on our half here we said the a value is 1/2. The thing to point out here is this: a graph that is wider tends to be a proper fraction for an a value. And recall that a proper fraction just means that the bottom is bigger than the top. And then if we had an improper fraction, improper would imply skinniness. Okay, improper fraction would be skinny. So if we say skinnier or wider than what? Then we say of our basic graph of y equals x squared that we've got over here, which had an a value of 1. So you might say, well, what if I had a graph that was not proper, not improper? What if I had like 4/4? X squared. Well, recall that anything divided by itself, where the top of the fraction and the bottom of the fraction are perfectly balanced, would just be y equals x squared. So the important thing to know about a is it adjusts the widths of our graph. It doesn't mess with the vertices, but adjusts the width of the graph depending upon how it compares to 1. Okay, so now the second set of graphs, just very quickly, we say we have negative a values. So we're going to pop back over here. We're going to very quickly kind of take these out. We say, well, our original graph was y equals x squared. Well, when we make y equals negative x squared, of course, we observed when we graphed it by hand that this is just a graph that is the same as the one up here, has the same width. But that negative one there has the same width, but it caused it to open downward. So if we were to type in now, input y equals negative 1/2 x squared. Remember, 1/2 is a proper fraction. We got a wider graph. Okay, so it had the same width as our graph of y equals 1/2 x squared, but it opened downward, or maybe even y equals negative 2x squared. So here's a skinnier graph, or y equals negative 5x squared, or negative 5/1, very proper fraction, or improper fraction, so very skinny. But you can see a adjusts the width, still just as it would up top, but the fact is it caused it to open downward. Okay, so if it is negative. So we're going to make a few quick statements about this and be done with this video, but we say down here at the bottom, we say describe the effect of a on the graph. We say, well, if, we'll do a couple of if then, we say if a is positive, then it opens upward, Okay, this is very true about our a value all the time, and if a is negative, then it opens downward, opens downward. Furthermore, we say if this is true about a, if the absolute value of a, which means I don't care if it's positive or negative, just if it's greater than 1. Another way of saying this is if it's an improper, then it's skinnier than the graph of, and we're always comparing it to the graph of 1x squared. It's skinnier than this graph. If now, however, this is true, we say a is somewhere between, the absolute value of a is somewhere between 0 and 1. In other words, we say a proper fraction, where the bottom is bigger than the top, then it is wider than y equals 1x squared. And we say if a is equal to 1, well, if the absolute value of a, we say equals 1, then we say normal width. This is our normal graph that we saw up here at the top. Okay, so very true about a, those things. So this is a basic rundown of what we mean by quadratic functions, their parabolas, and the effect of a upon the graph. Cheers.